So this one is Winter 23 paper 41, question 1. So the first question that you expect to see is either circular motion and or gravitational field. Sometimes it can be a combo. Okay, so let's read the question. Looks like this one is about gravitational field. State what is indicated by the direction of gravitational field line at a point in a gravitational field. So these gravitational field lines is basically a diagram way to represent the field. Currently, you are sitting inside the gravitational field, but you cannot see the field, right? So physicists decide that maybe we should draw some lines to show that A, there's magic in this space. No, there's no magic. There's just a force field, okay? And this direction of these lines tells me the direction of the force. So let's say if I have an object here, it will experience gravitational force in this downward direction. If I have an object here, it will experience attraction gravitational force towards the point mass. So it's very important to understand that the line here defines or tells us the direction of gravitational force acting on a mass placed at the point. So if at any random point, let's say this is point P, the direction of this line tells me the direction of where gravitational force will be. Okay, 1 mark. The keyword to include is direction of force acting on a mass at the point. Okay. Part 2. Explain with reference to gravitational field lines why the gravitational field near the surface of the Earth is approximately constant for small changes in height. So we've done this question before in some other past year question, but if I zoom in onto, let's say, this section of the Earth, it will no longer curve, right? And I zoom in some more, eventually it will look like a straight line. Okay, so I guess the first thing to talk about is the shape of the field pattern. Okay, these field lines are radial, meaning it will travel along the radius of the sphere, making all of this 90 degrees. So the gravitational field lines are radial, based along the radius. Since small changes in height is negligible. So when we're very, very close to the planet surface, right, they will look almost parallel. So you zoom in some more, eventually they will look like this. That's why Earth feels flat, but actually it's a sphere because the radius is very big and your height is negligible. Your perspective is negligible. So small changes in height is negligible when compared to the radius of Earth. Field lines will then appear to be parallel. Hence, the field strength is constant or approximately constant. Okay, because the gap between the lines tell me how strong the field is. So when the gap is far, the gravitational field is weak. When the gap is closer, let's say close to the surface, the gravitational field is strong. But if the gap is the same and they are parallel, then the gravitational field strength is constant. So the takeaway here for the first section is to see whether students understand properties about how we draw field lines to represent the field. So the intention of section 1A is to basically understand field lines and how it's used to represent gravitational fields. Okay. All right. B, here's a large isolated uniform sphere, and it has a mass m and radius big R. Point P lies on a straight line across the center of the sphere at a variable displacement x from the center. Okay, sure. So basically P is just any point outside lah, but it's anywhere lah, just anywhere outside that I can measure x with. And this is the variation of gravitational field for values of x for which P is inside the sphere. Okay, so let me maybe draw the sphere for you here first so you can visualize it. I'm the kind of person where I like some context. So I'm just gonna sphere here. You may not need it if you're very good at visualizing. Well, I'm not. I'm not a very diagram person. I think maybe in another parallel dimension, I will be a science fiction writer instead of a teacher. Because I think in words more than pictures. Okay, anyway, this distance x is measured out from the sphere, negative x. Okay, which means when your point at this point here, just interpreting the graph for the people, at this point here, x is equal to the radius r. At this point here, x is equal to negative r. So inside the surface, our gravitational field is uniform, right? This is plucking from this graph, G against R. Inside is straight line, outside is like that. This is your sphere. Okay. So outside G is inversely proportional to R squared. Inside G is proportional to R. Okay. The magnitude of gravitational field strength at the surface is Y. Okay, like I said, they can use any alphabet they like. Determine an expression for Y in terms of M and R. Identify any other symbols that you used. Well, magnitude of gravitational field is gravitational field strength because it tells us how strong the gravitational field is. So Y is equal to G, but to calculate G, it would be Gm over R squared. Okay, so this one is at the surface. So I guess R is the radius of, is this a planet? Just a random sphere. Okay, radius of sphere, m is mass of sphere, and G is gravitational constant. So the question is very theoretical, okay? They are asking whether you can write down the expression for gravitational field strength, 1 mark. And if you define any other symbols that they didn't define, which is capital G, 1 mark. Okay, moving on. Explain why at the surface of the sphere, G always have opposite sign to X. So your gravitational field strength G, right? This one is a vector. So opposite sign to X means opposite direction. But why is it opposite direction? Well, let's look at the diagram. If let's say I have an object here, the object will be attracted to the center of the sphere G. Although this is the direction of FG lah. Just like if I have an object here, it'll be attracted to the center of the sphere G. So because G and X is always opposite direction, so you can see, let's say I look at the right side, X is pointing to the right, positive, but G is pointing to the left, so negative. So in physics, right, we use positive and negative sign for many things. Told you many times before. If this is a vector, positive and negative sign is for directions. So let's pass. Okay, so I guess the important points will be their opposite direction. And the reason why they're opposite direction is because gravity is always attractive. The field lines is always directed towards the center. Okay, so gravitational field strength and gravitational force is opposite to the direction of displacement. This one is G. Displacement X. This is because gravitational force is always attractive. Or you can say always act to the center of the sphere. X towards the center of sphere. So if you show an understanding that the positive negative sign for this one is about direction, this is 1 mark. You mentioned one can already lah. Either field strength or force is opposite to the direction of displacement, 1 mark. And then the second mark would be gravitational force is always attractive or they always act towards the center. And finally, part 3, complete the graph to show the variation with G and X for values of X up to 3R, for which point P is outside the sphere. So for outside the sphere, it's quite easy to draw one because outside the sphere, G is equal to Gm over R squared. Inside the sphere, G is equal to, I mean, I've derived this before, but if you want to, you will have to derive again. G over R squared. But density is mass over volume. So mass is density times volume. So G would be G, density of the Earth, volume of the sphere would be 4 over 3 pi R cubed divided by R squared. So one of the R obviously can simplify, right? So inside the sphere, my G is equal to 4 over 3 pi rho G R. This whole thing is constant. That's why G is proportional to R. That's why you get a straight line. That's the magnitude. Direction, we will have to consider separately. The sign, the negative sign only comes in when you draw the diagram and decide the direction. However, for this one, because G and M is constant, same mass, same G, so G is proportional to 1 over R squared. Okay. Of note here, inside, right, M is not constant because when you are inside, the amount of mass that attracts you becomes less. Let's say the object is here. So the amount of mass that attracts you is the one that I shade, not the whole thing. But then when you are outside, draw a circle. When you're outside, let's say you are here, then the amount of mass that attracts you will be the whole thing. So M constant outside the sphere. Inside the sphere, M not constant. But regardless, G and M in constant, and they're asking us for outside the sphere. So G would be inversely proportional to R squared. Let me go back to the graph. If G is inversely proportional to R squared, and this one is Y, if you generally struggle with this, right, let me show you what to do. Here to here, your R times 2, correct? So this means it's inverse. So when one becomes bigger, multiply by 2, the other one becomes smaller. This one will multiply by 1 over 2. But because of the square, multiply by 1 over 2 square, which is equivalent to multiply by 1 over 4, which is equivalent to multiply by 0.25. So 0.25 would be here. Okay, so radius multiply a factor of 2, then gravitational field strength will multiply by a factor of 1 over 2 square because of this relationship. Okay, we can keep doing it for R. Of course, I'm going to refer back, for 3R, I'm going to refer back to R. So here multiply by 3, right? So meaning here to here, we will have to multiply by 1 over 3 square, which is 0.11 or 1 over 9. So 0.11 would be 5. So this is 0.1. 2 boxes, right? Because 1 box is 0.05. Yeah. Teacher, why is it negative? Well, because on the right side of the graph, the gravitational field is attracted to the left. So negative. So now you have these chords, you can plot them, join them with an inverse square curve. For paper 4, we must be able to see that your pencil passed through all these important points, okay? Something like that. All right, we're going to repeat everything here, but I don't really have to. So 2R will be quarter, and 3R will be 0.1. This one will be in the positive direction because when you're on the left side, the mass is attracted to the right. So with a smooth pencil, draw a x square, 1 over x square curve. Okay. So all I need is to see a decreasing gradient, right? If it's not very smooth or not very perfect, it's okay. The 3 mark will be 1 mark. I see this curve. I see this curve. The gradient decreasing. 1 mark if it's the correct quadrant. So those of you who don't do maths, quadrant means I draw it here. I never draw anything like here. This will be the wrong quadrant. This blue color will be the wrong quadrant. But correct shape, still get the first mark. This one is shape. Okay. This one, correct shape. Wrong quadrant. Okay. And one more mark is the coordinates. Did you pass through this coordinate and this coordinate and this coordinate? Need to pass all these 3. If you didn't pass any of these coordinate, you will lose the 3rd mark. So for paper 4, we anticipate that you sketch at least 2 graphs, 3 graphs. And normally they come with a lot of marks because we want you to show a lot of details. So if you know how to sketch them, it's quite a nice bonus. So this whole question is 10 marks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 marks. Okay. So I'm going to follow up with this question by talking about some places that I think the question can go. For example, if I drill a hole or a tunnel across this section of the planet, okay, then the object will be in simple harmonic motion. So just this section in the inside, when it's a straight line, the object is in simple harmonic motion. Yet. But I think they're going to ask soon. They already give you the graph, maybe next round. Okay, so maybe your turn. Simple harmonic motion. Remember, simple harmonic motion, there are 2 important constants you need to find. Then this one becomes your amplitude A. This one also becomes, negative A. This one is positive A. And this maximum value is maximum acceleration, A max. So A max is A omega square. We can use this value here, to calculate omega. And then after that, you unlock all your simple harmonic motion equation. Okay, questions that are similar to this. Let me go hunt. I actually think that this is a pretty unique question. But if you want to focus on just the beginning part, just 1A, you can refer to Winter 20 P41 question 1. There will be a calculation that is around this question 1. Inside the planet, they've never asked yet. Can they ask? Sure. Okay, another similar one will be Winter 18 P42 question 1. Okay, inside the planet is new. Simple harmonic motion, ties have never been asked before. Can they ask? Yes. So just relate it to your regular simple harmonic motion graph.